Section: Contents. In this section, we outline our strategies to boost reasoning abilities during the pre-training of MiMo 7B. This includes how we construct the pre-training data, design the model architecture, and set hyperparameters. We also showcase the reasoning potential of the MiMo 7B base model. We have developed large language models, LLMs, with strong reasoning skills, such as MiMo 7B, which excel in complex tasks like math and code generation. These models are trained using large-scale reinforcement learning, RL, allowing them to learn advanced reasoning techniques, including detailed analysis and self-correction. This represents a significant step forward in artificial intelligence's ability to solve difficult problems. Most successful RL efforts currently depend on large base models, typically around 32 billion parameters, especially for improving code reasoning. It is generally believed that achieving consistent improvements in both math and code reasoning within smaller models is tough. However, we argue that the success of an RL-trained reasoning model hinges on the base model's inherent reasoning capabilities. To fully harness this potential, we must focus on both pre-training and post-training strategies aimed at enhancing reasoning. We introduced MiMo 7B, a series of models specifically designed for reasoning tasks. Our experiments with MiMo 7B base reveal that it has exceptional reasoning abilities, even outperforming larger models. We also conducted RL training on a newly started supervised fine-tuning (SFT) model, resulting in MiMo 7B RL, which shows superior performance in both math and code reasoning, surpassing OpenAI's smaller models. For pre-training, we optimized our data processing methods, improving text extraction tools and applying multidimensional filtering to enrich the reasoning patterns in our data. We generated a large variety of synthetic reasoning data using a three-stage mixture strategy, training MiMo 7B base on about 25 trillion tokens. We also added a multiple token prediction objective to boost performance and speed up inference. In our post-training phase, we compiled 130,000 math and code problems for RL training, ensuring they were verified for quality. We focused on using rule-based accuracy rewards to prevent reward manipulation. To address the sparse rewards for difficult code problems, we introduced a difficulty-based reward system, allowing for more effective optimization. We also implemented a data resampling strategy to improve sampling efficiency and stabilize updates during the later stages of RL training. To enhance our RL training and validation, we created a seamless rollout engine that integrates continuous rollout, asynchronous reward computation, and early termination, significantly speeding up training and validation times. We also improved the robustness of our inference engine within the RL system. In our evaluation, MiMo 7B base outperformed other open-source models of similar size, excelling in general knowledge and coding tasks. It scored 75.2 on the BBH benchmark, demonstrating strong reasoning skills. MiMo 7B RL0 exceeded the RL training performance of the larger 32 billion parameter model in both math and code tasks, highlighting its efficiency. MiMo 7B RL achieved an impressive score of 55.4 on the 2025 benchmark, outperforming OpenAI's smaller model by 4.7 points. In algorithm code generation tasks, MiMo 7B RL showed remarkable results, significantly surpassing OpenAI's smaller models in various tests, while also maintaining competitive overall performance. We are making the MiMo 7B series open source, including checkpoints for the base model, SFT model, and both RL models. We believe that this report and the models will provide valuable insights for developing powerful reasoning LLMs that can benefit the broader community. Section Summary. In this section, we outline our strategies for enhancing reasoning capabilities during the pre-training of the MiMo 7B model, including data construction, model architecture, and hyperparameter settings, ultimately demonstrating that MiMo 7B base exhibits significant reasoning potential. We emphasize the importance of tailored pre-training approaches to unlock the inherent reasoning abilities of language models. Section: Pre-training data. In this section, we describe our approach to pre-training data for MiMo 7B, which includes a variety of sources like web pages, academic papers, books, programming code, and synthetic data. We believe that using more high-quality reasoning data during pre-training can significantly improve the reasoning abilities of our language model. To achieve this, we first enhance our text preprocessing pipeline to boost quality and reasoning data density. Next, we utilize advanced reasoning models to create a large amount of synthetic reasoning data. Finally, we apply a three-stage data mixture strategy to optimize our model's reasoning capabilities across different tasks and domains. For better reasoning data extraction, we recognize that web pages often contain rich reasoning patterns, such as coding tutorials and math blogs. However, we found that standard extractors often miss important math equations and code snippets. To solve this, we developed a specialized HTML extraction tool designed for math content, code blocks, and forum sites. We also improved our PDF parsing tools to better handle STEM and code content, allowing us to preserve valuable reasoning patterns for later processing. Fast global deduplication is essential for enhancing training efficiency and minimizing overfitting. We implement both URL deduplication and min-hash deduplication across all our web page data. Thanks to our engineering optimizations, we can complete this deduplication process in just one day. Since deduplication algorithms do not differentiate between high and low quality text, we later adjust the final data distribution based on multidimensional quality scores. We understand that high-quality pre-training data with rich reasoning patterns is vital for building models with strong reasoning skills. We discovered that common heuristic filters often mistakenly remove high-quality web pages that contain significant math and code content. To overcome this, we fine-tune smaller language models to act as data quality taggers, performing domain classification and multidimensional quality assessments. Synthetic reasoning data is another important source of reasoning patterns. We use various strategies to generate diverse synthetic reasoning responses. First, we select STEM content with high reasoning depth and prompt models to create insightful analyses. We also gather math and code problems for reasoning models to solve, along with general domain queries, especially in creative writing. Our initial experiments show that synthetic reasoning data can be trained for many epochs without the risk of overfitting, unlike non-reasoning data. To optimize our pre-training data distribution, we employ a three-stage data mixture strategy during final model training. In Stage 1, we include all data sources except synthetic responses for reasoning tasks, downsampling overrepresented content like ads and news while upsampling high-quality professional data. In Stage 2, we significantly increase the amount of math and code-related data to about 70% of the mixture, enhancing specialized skills without losing general language abilities. Both stages are trained with a context length of 8,192 tokens. In Stage 3, we add around 10% synthetic responses for math, code, and creative writing tasks, while extending the context length to 32,768 tokens. This process results in a high-quality pre-training dataset of approximately 25 trillion tokens. Regarding model architecture, MiMo 7B follows a decoder-only transformer design and includes features like grouped query attention, pre-RMS norm, SWI-glue activation, and rotary positional embedding, similar to Llama and Qwen. We note that reasoning models often struggle with inference speed due to the lengthy auto-regressive generation process, despite the predictability of consecutive tokens in reasoning paths. To address this, we incorporate multi-token prediction, MTP, as an additional training objective, inspired by DeepSeek v3. This allows the model to plan and generate representations that improve the accuracy and speed of future token predictions. We implement different MTP setups for pre-training and inference. During pre-training, we use a single MTP layer, as our studies indicate that multiple layers do not provide additional benefits. However, we find that multiple parallel MTP layers can significantly speed up inference through speculative decoding. After pre-training, we duplicate the single MTP layer into two identical copies, and then, with the main model and the first MTP layer frozen, we fine-tune the two new MTP layers to enhance inference speed. Section Summary. In this section, we describe our approach to enhancing the MiMo 7B model's reasoning capabilities through a diverse pre-training corpus, optimized data extraction tools, and a three-stage data mixture strategy that prioritizes high-quality reasoning data. We also implement multi-token prediction modules to improve inference speed while maintaining the model's reasoning depth and accuracy. Section: MTP Inference Speedup. In this section, we discuss how MTP layers can be used during inference for speculative decoding, which helps to reduce the time it takes to generate outputs. We tested the performance of these MTP layers on 24 benchmarks. The first MTP layer has an impressive acceptance rate of about 90%, and even the third layer maintains an acceptance rate above 75%. This high acceptance rate allows MiMo 7B to improve decoding speed, especially in reasoning tasks that require very long outputs. For our model's hyperparameters, we set the number of transformer layers to 36, with a hidden dimension of 4096. The intermediate hidden dimension for the feed-forward network is 11008, and we use 32 attention heads along with 8 key value groups. Regarding training hyperparameters, we utilize the Atom W optimizer with specific values for beta parameters and a weight decay of 0.1. We apply gradient clipping with a maximum norm of 1.0. In the first two pre-training stages, we work with a maximum sequence length of 8,192 tokens, and in the third stage, we increase this to 32,768 tokens. Our learning rate starts with a gradual increase from 0 to a specific value over the first 84 billion tokens, remains constant for a while, and then gradually decreases. We also implement a linear increase in batch size to 2,560 during the first part of training, maintaining this size through the first two stages, and then fixing it at 640 in the third stage. The MTP loss weight starts at 0.3 and is reduced to 0.1 later in the training. For evaluation, we assess MiMo 7B base across various benchmarks, including natural language understanding, reasoning, scientific question answering, reading comprehension, mathematics reasoning, coding, and Chinese understanding. We compare our model with other open-source models of similar size, ensuring that all models are evaluated under the same conditions. To better understand reasoning capabilities, we adopt the pass at K metric, which counts a problem as solved if any of the sampled solutions are correct. Our results show that MiMo 7B base achieves significantly higher pass at K scores than all other models, especially as the number of samples increases, indicating its strong reasoning potential. In general reasoning tasks, MiMo 7B base outperforms other open-source models of similar size. For instance, on the BBH benchmark, it scores 75.2, which is about 5 points higher than Quen 2.5 to 7B. Additionally, our model demonstrates strong performance on graduate-level problems in Super GPQA and excels in reading comprehension on the drop benchmark, showcasing its advanced language understanding capabilities. Section Summary. In this section, we demonstrate that the MTP layers significantly enhance inference speed with high acceptance rates, enabling the MiMo 7B model to excel in reasoning tasks requiring long outputs. We also detail our model's architecture, training parameters, and evaluation setup, highlighting its superior performance across various benchmarks compared to similar-sized models. Section: Code and Mathematics Reasoning. In this section, we demonstrate that MiMo 7B base excels in coding and mathematics tasks. On the live code bench V5, it achieves a score of 32.9, significantly outperforming LLAMA 3.1 to 8B and QWEN 2.5 to 7B. Similarly, on the 2024 benchmark, our model again scores 32.9, showing its superiority over other models of similar size. These findings emphasize MiMo 7B base's exceptional problem-solving skills and its potential for complex reasoning tasks. We recognize that understanding and reasoning over long contexts is crucial for modern models, as it allows for the creation of intricate reasoning chains. For the needle in a haystack tasks, which focus on retrieving information from long contexts, we analyze accuracy across different depths and context lengths. Our observations reveal that MiMo 7B achieves nearly perfect retrieval performance within a 32,000 token context window. Beyond retrieval, MiMo 7B also excels in long context reasoning tasks, such as extracting common and frequent words and tracking variables, outperforming Qwen 2.5-7B in most cases. These results confirm the effectiveness of our approach to include diverse, high-quality reasoning patterns during pre-training. After pre-training, we implement post-training on MiMo 7B base. We create MiMo 7BRL0 through direct reinforcement learning from MiMo 7B base, and MiMo 7BRL is trained from a supervised fine-tuning version of MiMo 7B. Our supervised fine-tuning, SFT, data combines open source and proprietary distilled data. To ensure quality and diversity, we follow a three-stage preprocessing pipeline. First, we remove any training queries that overlap with evaluation benchmarks to avoid data leakage. Next, we exclude samples with mixed languages or incomplete responses. Finally, we limit the number of responses per query to 8, balancing diversity and redundancy. This results in a final SFT dataset of about 500,000 samples. We fine-tune the MiMo 7B base model using a constant learning rate of 3 × 10⁻⁻5 and a batch size of 128. During training, we pack samples to a maximum length of 32,768 tokens. For our reinforcement learning (RL) data, we focus on two types of verifiable problems: mathematics and code. Our initial studies indicate that high-quality problem sets are essential for stabilizing the RL training process and enhancing the model's reasoning abilities. Our mathematical problem set is sourced from various open-source datasets and proprietary collections. To prevent reward hacking, we use a language model to filter proof-based and multiple-choice problems. Unlike some recent methods that alter problems for integer answers, we keep the original problems intact. We also perform global deduplication and carefully clean our problem set against evaluation benchmarks. We assess problem difficulty using a model-based approach, filtering out those that are too hard or contain incorrect answers. For the remaining problems, we run an SFT version of MiMo 7B multiple times, removing problems with a pass rate above 90%. This process eliminates about half of the easier problems, resulting in a mathematical training set of 100,000 problems. For coding problems, we compile a high-quality training set from open-source datasets and our own collected problems. We discard problems without test cases and exclude those with golden solutions that fail to pass all test cases. For problems lacking golden solutions, we remove those that cannot be solved in 16 attempts by advanced reasoning models. Similar to our math data, we use an SFT version of MiMo 7B to filter out easy problems that are solved perfectly in all attempts, leading to a final set of 30,000 coding problems. During each RL iteration, we evaluate thousands of problems to calculate rewards, with each problem potentially containing numerous test cases. To enhance efficiency and reduce idle GPU time, we developed an online judge environment for parallel execution of high-volume unit tests. In our training process, we utilize only rule-based accuracy rewards. For mathematics, we apply the Math Verify library to assess correctness. For coding problems, we implement a reward system based on test difficulty, as detailed in our paper. We do not include additional rewards, such as format or length penalties. Section Summary. In this section, we demonstrate that MiMo 7B base excels in coding and mathematics tasks, achieving high scores on benchmarks and showcasing strong long context comprehension and reasoning abilities. We detail our rigorous data curation and preprocessing strategies for both mathematical and coding problems, ensuring high-quality training sets that enhance the model's performance during reinforcement learning training. Section RL training recipe. In this section, we describe our approach to reinforcement learning, RL, training. We utilize a modified version of Group Relative Policy Optimization, GRPO, that incorporates recent improvements from the research community. For each problem, we sample a group of responses from the old policy and update the policy by maximizing a specific objective, using two hyperparameters to guide the process. The advantage for each response is calculated based on the rewards received. We have made several enhancements to the original GRPO algorithm. First, we removed the KL loss, which allows the policy model to reach its full potential without sacrificing stability. Second, during the rollout phase, we oversample and filter out prompts that either always succeed or always fail, ensuring that all prompts in the batch contribute effectively to training while keeping the batch size consistent. This method helps adjust the difficulty of problems throughout the training. We also increased the upper clipping bounds while keeping the lower bounds fixed, which helps the policy explore new solutions and addresses the issue of entropy convergence. Throughout training, we identified two main challenges: sparse rewards for coding problems and reduced sampling efficiency. To tackle these, we introduced a reward function based on test complexity and a method for easy data resampling. For our reward mechanism, inspired by the International Olympiad in Informatics, IOI, we propose a test difficulty-driven reward. In IOI contests, problems are divided into subtasks, and participants earn points for each subtask completed. This approach allows our model to receive partial rewards for solving some subtasks in difficult problems, enhancing learning from challenging cases. We also developed a technique to categorize test cases by difficulty based on their pass rates. By running multiple rollouts, we calculate the pass rate for each test case and group them accordingly, with lower pass rates indicating higher difficulty. Our findings show a clear distinction in test difficulty, with more capable models achieving higher pass rates. After categorizing tests, we created two reward schemes: a strict scheme, where a solution earns rewards only if it passes all tests in its group and lower groups, and a soft scheme, where the total score is shared equally among tests, with the final reward being the sum of scores for all passed tests. We compared the performance of these schemes against a baseline without the difficulty-driven reward. To address sampling efficiency during training, we noticed that as our policy improved, more problems achieved a perfect pass rate, leading to their exclusion from the batch. Instead of removing these problems entirely, which caused instability, we developed an easy data resampling strategy. We maintain a pool of problems with perfect pass rates and sample from this pool with a certain probability during rollouts. This approach stabilizes policy updates and enhances sampling efficiency, particularly in the later stages of training. Section Summary. In this section, we describe our modified Group Relative Policy Optimization, GRPO, approach, which incorporates enhancements like dynamic sampling and a test difficulty-driven reward mechanism to improve training efficiency and model performance on algorithmic code generation tasks. We also introduce a resampling strategy to maintain stability and efficiency during training by utilizing an easy data pool of problems with perfect pass rates. Section: Hyperparameters. In this section, we describe our hyperparameters and the infrastructure we developed for our experiments. We used a training batch size of 512 and an actor mini batch size of 32. Each training iteration included 16 gradient updates with a learning rate of 1/1,000,000th. We set the maximum sequence length to 32,768 tokens to support complex reasoning tasks. During training, we configured both the temperature and top P parameters to 1.0 to enhance output diversity. We created the seamless rollout engine to improve the robustness of VLLM for efficient dynamic sampling-based reinforcement learning, RL, training. Our RL system is built on Virl, an open-source RL training library that utilizes Ray for managing computation and communication. This setup allows us to implement rollout and training phases using Ray actors and share training data through Ray objects. However, we noticed that Virl experiences GPU idle time during rollout and reward computation due to uneven response lengths, which leads to wasted computational resources and slows down training. Previous works have addressed this issue with system-level solutions, but many rely on asynchronous training, which can alter the algorithm and introduce delays in long sequence responses. Additionally, computing rewards based on code data is time-consuming, causing further idle periods for GPUs. Our approach of dynamic sampling, while enhancing sample efficiency, also increases GPU idle time and results in wasted examples during multi-turn rollouts. To tackle these challenges, we developed the seamless rollout engine, which optimally fills sample batches during rollout while performing asynchronous reward computation. We built this system on the VLLM inference engine and collaborated with the open source community to strengthen VLM's external launch mode within the Virl framework. We also implemented MTP in VLLM to support both MiMo 7B and MiMo 7B RL. The seamless rollout engine enhances GPU utilization in rollout workers through effective task scheduling, reducing idle time during continuous operation. It includes three main components: continuous rollout, asynchronous reward computation, and early termination. This engine achieves a speedup of over 2 times in training and nearly 2 times in validation. The continuous rollout component focuses on efficiently managing completed rollout tasks and starting new ones. Unlike basic dynamic sampling methods that wait for all workers to finish before computing rewards, our engine removes synchronization delays between the generation and reward phases. It actively tracks completed tasks, computes their rewards immediately, and initiates new rollouts as needed. After calculating rewards, we update the valid sample count and pass rate statistics, launching new tasks if current ones are insufficient. For asynchronous reward computation, we found that while rewards for math data are computed quickly, evaluating code-related data takes much longer, leading to GPU idle time. To address this, we use Ray to manage reward computation concurrently with rollout tasks. Once tasks are done, the system either sends rollout outputs for reward evaluation or aggregates results to update the sample state. We also allocate dedicated servers for code-specific reward computation to avoid bottlenecks. In terms of early termination, when we have enough valid samples, we must manage ongoing tasks carefully. Abruptly stopping tasks can hinder the generation of long sequence responses, which is crucial for stable RL training. Instead of waiting for all tasks to finish, we use a first-in first-out strategy, terminating tasks only when the valid sample count meets the batch requirement and all earlier tasks are complete. For our experimental analysis, we randomly selected a 5-step training trace to assess the seamless rollout engine's performance on 256 H20 GPUs. We measured overall speedup for RL training efficiency, rollout speedup for task acceleration, and normalized GPU idle time. We also calculated the GPU idle ratio and sample waste ratio. Our results show that while the experiment without dynamic sampling achieved higher throughput, it resulted in significant sample inefficiency due to many zero-gradient training samples. These samples reduce the effective training batch size and can destabilize RL training dynamics. With a sample pass rate of 41% in this experiment, static sampling performed similarly to naive dynamic sampling, but the latter avoided zero-gradient data and reduced wasted samples. The seamless rollout engine, with all its components, achieved comparable one-step training times to static sampling while demonstrating better sample efficiency, reducing the sample waste ratio from 22% to around 15% through continuous rollout and dynamic scheduling. Section Summary. In this section, we detail our experimental setup using a training batch size of 512 and a maximum sequence length of 32,768 tokens, while introducing the seamless rollout engine to optimize GPU utilization during reinforcement learning training by minimizing idle time through continuous rollout, asynchronous reward computation, and early termination strategies, achieving significant speedups in both training and validation. Our analysis shows that this engine enhances sample efficiency and reduces waste compared to naive dynamic sampling implementations. Section: Accelerated Validation. In this section, we discuss our approach to accelerated validation and evaluation of our models. During validation, we stream the rollout and reward tasks using the seamless rollout engine. We set the validation batch size to match the dataset length and run all rollout tasks at once. By using asynchronous reward computation, we achieve nearly double the speed while keeping GPU idle time to just 25%. Our results show that the seamless rollout engine can effectively handle static sampling, allowing for one-pass rollout and reward computation. If the validation dataset is large enough, we can further speed things up by optimizing the batch size and using continuous rollout. For inference, we utilize the VLLM engine and have added new features to support our model. We have also integrated MTP modules to improve performance and made MTP support available for efficient inference in MTP-equipped architectures. To enhance robustness, we have addressed stability issues in the external launch mode of VLLM. We ensure consistency in KV cache by clearing computed blocks during preemption and disable asynchronous output processing when increasing scheduler steps. In our evaluation setup, we assess reasoning models across various benchmarks, including language understanding, scientific question answering, instruction following, reading comprehension, mathematics reasoning, and coding. We set specific parameters for sampling temperature and maximum generation length for different benchmarks. We compare our MiMo 7 BRL model against several strong baselines, including both reasoning and non-reasoning models. The evaluation results show that MiMo 7 BRL performs exceptionally well in mathematics reasoning, closely following the top model in its category. In algorithm code generation, it significantly outperforms other models, achieving impressive scores on live codebench. Overall, MiMo 7 BRL demonstrates strong general performance, surpassing several competitors. We also present results for different versions of MiMo 7B, noting that MiMo 7 BRL0, trained from the base model, shows a strong growth trend, while MiMo 7 BRL, trained from the SFT model, reaches a higher performance ceiling across all benchmarks. In our discussion, we share insights from the post-training process of MiMo 7B. We found that during the initial RL training from MiMo 7B base, the model focused on adapting the answer extraction function. We explored a lighter SFT approach to help align the model with the expected answer format. However, this lighter model, MiMo 7 BRL Lite SFT, did not perform as well as anticipated, trailing behind both the base model and the heavier SFT model after a short period. Section Summary. In this section, we describe our implementation of the seamless rollout engine for accelerated validation, achieving a 1.96x speedup and reduced GPU idle time through asynchronous reward computation. We also evaluate our MiMo 7 BRL model across various benchmarks, demonstrating its strong performance in mathematics reasoning and coding tasks, while discussing the impact of different training approaches on model performance. Section: Interference between different domains. In this section, we discuss the interference between different domains during the later stages of reinforcement learning (RL) training with MiMo 7B base. We find it challenging to maintain a balance in performance between mathematics and coding tasks. Between training steps 2000 and 2500, we notice that the model improves continuously on coding problems, while its performance on mathematical reasoning tasks varies and declines. In contrast, when we train the cold-started supervised fine-tuning (SFT) model, we see consistent improvements in both areas. Our analysis shows that the base model, which has strong exploration abilities, tends to exploit rewards for math problems. However, for coding tasks, the test case-based verifier makes it much harder to exploit rewards. This emphasizes the importance of having high-quality math problem sets for effective RL training. We also observe language mixing issues during RL training on MiMo 7B base, similar to what we saw with DeepSeek R10. To address this, we introduce a language mixing penalty in the reward function. However, we find it difficult to design this penalty effectively. While it is easy to spot Chinese characters in English responses, detecting English words in mathematical equations and code is much harder. Consequently, the penalty does not completely solve the language mixing issue and may lead to reward hacking, where the model generates English responses regardless of the language of the question.